Okay, so let us get started.
Thank you very much. It's a great honor for me to be at this conference. First met Sasha in some crazy year, 93 and 94, when he visited my advisor, Joseph Bernstein, in Tel Aviv. So Sasha belongs to this generation of mathematicians exactly between my advisor and myself. And so like Bellens and many others. And for me, the generation represented the guys that I really want to be like. So they were role models for me throughout my career. And so Sasha has many amazing qualities. One of them is his mathematical versatility, how he is interested and produces work in many areas of math. So by contrast, I've been stuck on the same problem for 25 years, and this talk will be in the same vein. And moreover, I've given this kind of talk many times over the last 2 years, and now I feel like I need to apologize. I mean, I don't have anything else to talk about. I've been writing this humongous paper for 2 years, and I don't have anything else. All right, so let me get started with the math. So the topic is still the geometric Langlands conjecture. The good news is that I think it will become a theorem, the whole thing will become a theorem very, very soon. But I don't want to announce it formally. Okay, so let me remind you the two kind of well-known forms of the geometric Langlands conjecture. So let X be a curve over a ground field K, and so K has different versions. So it can be, let's say, it'll be the Rham context, in which case K is just characteristic 0. There is a Betti context, in which case K equals C, and there is étale context, in which case K is arbitrary. And so this context dictates what kind of sheaves we'll be dealing with. So here we'll be dealing with D modules. And D modules is a category which is linear over the same ground field. So it's a category over K. So here we'll be dealing with all topological sheaves, and we call it Betti sheaves. And the coefficients of these sheaves can be arbitrary. Because I'm a chicken, I'll take this sheaf, the coefficients to be a field of characteristic 0. But a more courageous person would take them arbitrary ring, and I'll call this field E. And here we'll be dealing with étale sheaves, elliptic sheaves, and the coefficient will be Q bar. All right, so. And I'll first state the geometric Langlands conjecture in these two contexts. So, and here is what it says. And so, yeah, G, so G is a reductive group over K, and its Langlands dual is a reductive group over the field of coefficients. So in all cases, I'll denote the field of coefficients E, but so it is K, this case, it's just some E here and Q bar here. So the de Rham versions reads as follows. So the goal is to describe the category of automorphic sheaves. And so we write D modules on what we call bun G. Bun G is the moduli stack of principal G bundles on the curve, and the Langlands conjecture predicts that it's the following. So I'll first write slightly incorrect thing. We consider quasi-linear sheaves on the stack of de Rham local systems. with respect to G check on my curve. So I'll remind you what it is in about 10 minutes. It's a kind of algebraic stack, but it's derived algebraic stack in general. And for it makes sense to consider quasi-Categorical sheaves, but unfortunately, this is not quite correct. And what one has to do, one has to replace it by called incoherent sheaves. That's a difference between perfect complexes and coherent complexes, which has to do exactly with singularities here. But the singularities of this stack are not so bad. It's not smooth, but it's in which case there wouldn't be any difference. But it's what we call quasi-smooth. It's derived locally complete intersection. And in this case, one can quantify the difference between incoherent sheaves and quasi-coherent sheaves, but what's called coherent singular support. And so I'll write some symbol. We say that coherent singular support is a nilpotent. So, I mean, I will not go further into this side of the story because it's not the focus of my talk. So it described in detail, for example, paper of Dimarint and myself. So if you don't know what these guys are, just replace it by quasi-coherent sheaves and you will not lose anything from the contents of this particular talk. So this is the Rham context. So now let me say what happened to the Betti context. So the right-hand side stays exactly the same. The difference is that instead of the Rham local systems, we consider another algebraic stack, namely of Betti local systems. Let me point out that so these stacks are algebraic stacks over the field of coefficients. This guy E. So the categories on the right-hand side are E linear categories, as they're supposed to be, because our sheaves are E linear categories. So now let me say what appears here. And so this form of the Langlands conjecture was proposed by Betti and Madler, and they say the following. So they still, the geometric object Bungie, they consider all Betti sheaves, but not all of them. So what they discovered is that you will realize that this must be the case by looking at the case when G is GM, in which case you're dealing with the Picard. So they have to restrict the singular support. So also write nilp. Let's not confuse these two nilps. This is coherent singular support. This is kind of topological singular support. Just they happen to be the same for reasons that nobody, I think, quite understands. At least I don't understand. But let me say what this is. So in general, if you have an algebraic variety or a stack Y, you can consider its cotangent bundle. And if you have any subset here inside the category of sheaves, Y you can consider in the subcategory when you restrict the singular support. And you can also do it for D modules, as will same context. Yeah, in this case, so our sorry, something got into my eye. Y is Bungie, and T star Y is what's called the stack of Higgs bundles. And so let me not go into this discussion, but inside Higgs bundles, there's a pretty obvious notion of what it means to be nilpotent. And so so nilp is a subset, in fact, a Lagrangian subset inside Higgs. And so we restrict the singular support. Okay, so now, so that what has been known. However, my interest here is to come up with a version of the geometric Langlands conjecture that makes sense for L-adic sheaves. And the reason for doing so is that if we manage to come up with a conjecture, and if we take our ground field to be FQ bar with a Frobenius, we have a hope of connecting this theory to the classical theory of automorphic functions. All right. So kind of the nice proper aspect of what I'm going to do. So this will pass on to the restricted version of geometric Langlands conjecture, and that's uniform across all contexts. So it makes uniform sense with the Rham, Betti, and étale. So, and basically the question that I want to ask myself is, what do these two categories have in common? So in what follows, let me introduce a piece of notation. I'll be writing sheaves for the following thing. So sheaves on schemes, what I'll need is inconstructible sheaves. So S is a scheme in any of these contexts. So let me say what I mean by constructible. It means the following. It's in the Rham context, it's holonomic or holonomic regular singularities. So there are two versions here. In the Betti context, it would mean just if you have a variety over C, it makes sense to consider constructible sheaves in the usual sense. Constructible Betti. And in the étale context, also constructible in the usual sense. And so that's how. So that's what I mean by this category. Then you incomplete. This is just because I like to work with categories that have all co-limits. And so this is for schemes, but I'm also dealing with stacks. So the formal definition is this, that sheaves on a stack Y is, let me write this scary symbol. It's an inverse limit over all schemes mapping to Y of sheaves on S. In other words, an object of this category is a compatible family of objects of corresponding categories of objects with the corresponding categories on S's, compatible with respect to either sheet pullbacks or star pullbacks. There are two versions of the definition, but they turn out to be equivalent for reasons that's pretty obvious. All right, so that's what I want to do. And and I want to, and again, my ultimate interest in is the étale context. So I want to consider sheaves of G. So I consider this inconstructible context. But it's pretty clear from kind of, if you try to combine these two notions. So here I'll consider just holonomic guys. So basically, kind of the common denominator of these two things is sheaves nilp. So I'm considering the inconstructible context, but restricting single support. Here, a comment is necessary. So if you are in the Betti context, if you have a, well, restricting single support makes perfect sense because after all, these are still D modules. If you're in the Rham context, if you are in the Betti context, it still makes perfect sense to restrict because after all, these are Betti sheaves. Now, it turns out that one can make sense of single support also in the étale context, and this is due to the work of Sasha Bellinson, who 6 years ago, it was a major breakthrough. He defined what it means. So he proved that single support is well defined also for étale sheaves. So, so this is my left-hand side, and the question is, the Langlands conjecture will predict that it will be what? So it will be incoherent sheaves, put a single support, but on some new geometric object. So note that even in these two contexts, I've modified my left-hand side. So instead of all G modules, I'm considering in holonomic ones. Here, instead of all Betti sheaves, I'm considering with prescribed single support, I'm considering all inconstructible ones. So the right-hand side has to change accordingly. And so here, this new geometric object will appear that I'll call, so it's still local systems, but a different object. I call restricted. And now I'll explain what this means. So note that in the context of étale sheaves, so we actually don't, so there is no classical notion of the modular space of local systems in the étale context, because we don't know how to vary étale sheaves and families. The problem is that, so étale sheaves are, by their definition, constructed as inverse families of with finite coefficients, and we don't know how to vary such things over a base with positive Kroll dimension. So now I'll introduce what I mean by this. Define this object. All right. Restricted. So, and I'm going to explain what this means. So to do so, let me first remind you the definition of local system theorem and local system Betti. So, and we'll define them as functors of points. So I want to say that what is home from a test affine scheme S to log sys theorem first. And so where S is a test scheme over the field of coefficients, so S is spec A. So here is the definition. This is the following. This is symmetric monoidal functors from the following, from the category of algebraic representation Rham check to the following category. So I can say A modules within the category of D modules. And I should say right T exact. Whatever definition of the Rham local systems you take, if you unwind it and use the Tanakian formalism, you'll arrive to this definition. And I'll massage it a little bit in a second. So say one more time.
What are the letters of the?
So A mod within the category of D modules. So in other words, the D modules with an action of A. S is spec A. So it's an affine scheme. So now let me spell out the definition of the Betti guy. It'll be exactly the same thing. The only thing that the target category will change. So it will be symmetric monoidal functors from Rham check to A modules, but the target category will be, so we can take either of the following. So you can take
A is over E.
Over E, exactly, over the field of coefficients. So the stack of local systems lives over the field of coefficients. So in here, the target category changes. So these are Betti sheaves that are locally constant. In fact, you can show that if you have a symmetric monoidal functor to just Betti sheaves, it will automatically be, you'll hit locally constant ones. So these are local systems, but potentially of infinite rank to allow room for A modules there. Okay, and so now Betti.
It's upper and the lower.
Locally constant. So just local systems, a potential of infinite rank. So and now I want to introduce this guy, looks is restricted. But for this, I'll have to rewrite the right-hand side in both these cases to motivate my definition. So, and here, so the Lurie style higher algebra comes into play in a serious way. So we should note that if you consider A modules within some category, see some linear categories, call it DG categories, this is the same as the Lurie tensor product of the category of A modules, tensor C. In fact, so if you don't know the definition of Lurie tensor product, the left-hand side is more or less the definition. But the point is that it's Lurie tensor product is defined abstractly for a pair of DG categories. And so here comes the definition of locus is restricted. So we consider my category that I call sheaves. These are the inconstructible sheaves on my curve in any of the three contexts. It can be int holonomic, constructible Betti, or elatic. And inside here, I consider the locally constant ones. So, and I also use the following notation. I call them quasi-lease. So, and if you try to unwind this definition, so it's actually important to give the to have the right category here, otherwise the theory doesn't work. So let me try to just parse this for you. So what is quasi-lease? So it's the following. So first of all, it's an inconstructible complex on the curve. So in other words, so let me give myself F sheet here, object. So when does it belong to this subcategory? So here's what needs to happen. So we're taking its perverse cohomologies. So for every k, let's consider the perverse cohomology of F. It's an object of the abelian category, so int perverse sheaf. And what I need this int perverse sheaf to be in the local system. So it must be just a union of finite rank local systems. So I wrote it in this detail because the order of operations matters. So it's not true that F itself, so it's an inconstructible sheaf, but it's not true that it's in the local system. So it's only an int object at the level of individual cohomologies. Somehow this is important if you try to actually work with this object. So that being said, keep the geometric conjecture up there. So the definition of locus restricted is the following. So from S to locus restricted is exactly as before, write exact symmetric monodal functors from refg check to the Lurie tensor product of a mod with this category released. So all I did vis-a-vis the previous two contexts, I replaced my target category. So the former case was D modules. So the Rham case it was D modules. The Betti case it was Betti locally constant Betti sheaves. And in the restricted context, I replaced this target by the category of this id least sheaves.
You still want, right, the exactness?
Yeah. Right, it's the exact. All right. So now I have to say a few words about the nature of this geometric object. It's Loxis restricted. So on the one hand, it may appear utterly stupid. So let's take an example. Suppose G equals GM. And so let's start from scratch. So we know what individual local systems are in this inconstructible complex. And a priori, we don't know how to vary them in families, but we know how to do formal deformations. So you can, and the claim is that in this case, so this Loxis restricted, in the case of GM, is this completely stupid object. It's disjoint union over sigma. These are isomorphism classes of rank 1 local systems of the following. So pretend that local system exists, but pretend that it exists in some kind of usual sense, and take the formal completion of it as sigma. So what I'm saying is that if you have just a local system, even in the Elatic context, you can make sense of the formal scheme, which is just the formal neighborhood. And this local system restricted is a stupid object. It's like really kind of different isomorphism classes of local systems sit completely separately. Perhaps this is the reason why this object has been ignored for many years, because it really looks too naive to be useful. But it turned out to be actually very useful. All right, so now let me say just a few words about the structure. What can one say about this Loxis restricted in general? So let me say that in the previous two contexts, so consider Loxis de Rham, you can always write it as follows. If you choose a point on the curve, you can introduce a rigidification to this point. So you can write Loxis de Rham, let me say rigidified, so level structure. We call it at some point, divided by the action of G check, and this guy is a scheme. And exactly the same thing happens in the Betti context. Loxis check Betti for the rigidification. And so here, this guy is a scheme. And in this case, this guy is an FX. And what you can prove in the restricted context is that you can also choose a rigidification and write it as a quotient, where this guy is a formal scheme. So in other words, it's a let me say it like this. Let me write it better. disjoint union, like here, of formal schemes. So what I mean by formal scheme is that you take an affine scheme, you take as a risky closed subset, and you complete this affine scheme along this closed subset. So in other words, it's the form spec R completed along some risky closed subset. In the case of GM, these closed subsets are set theoretically points, but for when the semi-simple rank is higher, the risky closed subsets are kind of positive dimensional, depending on what your sigma is. So let me also say that, okay, let me just. Okay, so I've introduced the geometric object of interest. Now one can state the first theorem. So this is still a conjecture, but we have the following, which is kind of strong evidence in favor of this conjecture, namely, so theorem, and okay, now I'm starting to state results. All of this is joint work with Arinkin, Kazdan, Raskin, Rosenblum, and Warshawski. So theorem is that there exists a canonically defined monoidal action of the category of quasi-coherent sheaves on this geometric object. On this category of sheaves with nilpotent single support. So I should have said that we have analogous theorems, not conjectures, in both the Rham and Betti context. And so the assertion of this theorem is that we also have this, we call it spectral action in this restricted context. So now this theorem already buys you a bunch of stuff. So namely, it has the following kind of remarkable corollaries. Yeah, I should have said that this disjoint union is, so one can also say what set parametrizes it. So according to semi-simplifications, so if you consider two field-valued points of this geometric object, they will belong to the same connected component if and only if their semi-simplifications are the same. So the consequence of this theorem is that this category of sheaves with nilpotent single support splits canonically as a disjoint union with sigma is isomorphism classes of semi-simple local systems of the sum-ends. Really a very non-trivial result. So until this theorem, we didn't know how this category of sheaves with singular support looks like, and now turns out that kind of the eigenconditions that have to do with different semi-simple local systems, kind of these corresponding subcategories don't talk to each other. It's really kind of a direct sum decomposition. So there's another corollary which is less obvious to see from here, but it has some implications, is that specifically in the Rham context, so all objects in, let me say, sheaves polynomial have radial singularities. So this was conjectured by Bellison and Drinfeld some 30 years ago, and it turns out to be true. So it's kind of it's a somewhat non-trivial corollary of this theorem. All right, and finally, so I want to give applications of this theory to connecting geometric Langlands context to the classical one. And the procedure by which I will connect the two is the procedure of categorical trace. So let me remind you the following context. So we all know that if you have a finite dimensional vector space with an endomorphism, you can take its trace. But this is a feature of just symmetric monoidal categories. So if O is a symmetric monoidal category, and little o is a dualizable object, and C is an endomorphism O, you can attach to it its trace, and it'll be an endomorphism of the unit object of your ambient symmetric monoidal category. And the procedure is exactly as in vector spaces. So here's your unit, and because so O is dualizable, so there is a canonical map from the unit to O tensor O check. Then you apply your phi along the first factor, you go to O tensor O check. And so because you're symmetric, this is the same as O check tensor O, and then there's an evaluation map back to the unit. The composition is an endomorphism unit. This is your trace. So, and we take O to be the symmetric modular category of DJ categories with Lurie tensor product. So, so therefore, if you have a DJ category which is dualizable, and most categories that you encounter practice are dualizable with an endofunctor, you will be able to attach to it its trace, which is an endofunctor of the unit object. The unit object in the category of DJ categories is the category of vector spaces, and it's an endofunctor of that is a vector space. So if C is dualizable, DJ category, P is an endofunctor, you can attach to it its trace, which is a vector space. So this is the procedure we'll be playing with. So let me give you an example of how this works. So let's say that C is the category of Betti sheaves on some, well, in this case, it can be topological space Y, and phi is, in fact, let me say phi upper star, where, well, this phi is just an endomorphism of Y. So lemma, in this case, so this trace is very computable, and here's what it gives: trace of phi upper star on the category of Betti sheaves Y will be so cohomology with compact supports on the fixed point set of T with constant coefficients. And let me actually run this computation for you, and you will see that it's something very non-trivial going on there when you do it. Well, to run this computation, we apply the definition, but to do the definition, we need to say something explicit about the duality. So the claim is that if you consider the category of Betti sheaves on a manifold, there is a canonical self-duality. So namely, it's defined as follows. So the category of sheaves is canonical of self-dual. And then we write the unit and the co-unit maps. So the co-unit map is very easy to write. So it's a functor from here to the unit in our DG category, which is the category vector spaces, and it looks as follows. You take two sheaves F1 and F2, and you send them to the following. You consider cohomology with compact supports on Y of their tensor product. Tensor product in the usual sense. So this is the evaluation map. The unit map is kind of uses something deep, which one may overlook, namely the following. So the claim is that if you have two reasonable topological spaces, there is a procedure of external tensor product. You can take sheaf on the Y1 and Y2 box times and produce a sheaf on the product. And the claim is, again, this is in the sense of Louis tensor product. And the claim is that this functor is an equivalence. In particular, sheaves on Y, tensor sheaves on Y is the same as sheaves on Y times Y. And using this isomorphism, one can produce the unit. So the unit is the following. So the functor from vect to any target is the same as to specify an object of this target. And we first go to sheaves on the product. And the object you put here is delta lower shriek of the constant sheaf on the diagonal. So it's really kind of constant sheaf on the diagonal, shriek extended. And then you identify it by means of this non-trivial isomorphism, which naturally goes from right to left. You're kind of inverting this arrow, which is non-trivial. And it's easy to see that, so this evaluation in this unit produce a datum of duality. So given that, let me run this computation. So I'll write a diagram in which upper arrows I'll be taking star pullbacks along vertical arrows and shriek push forwards they're along horizontal arrows. So I start with a point. Here I'll write Y. So it will be Y times Y. Lower it. So this is the diagonal map. This map is phi times identity. This is again the diagonal map. And if you trace, like if you apply this definition using the datum of self-duality that I wrote up here, you will see that the trace of this phi upper star is the following. You pull back, you shriek push forward, you star pull back, you star pull back, you shriek push forward. However, there is base change for shriek push forward and star pull back. And so this diagram can be replaced by this diagram. And so what you do, you star pull back, you shriek push forward, and this exactly gives you this answer. Okay, so why did I bother to go into this example is that you may want to do the same, but in the inconstructible complex context. So let's Y be an algebraic variety or a stack with an endomorphism phi, and let's try to compute trace of phi lower upper star. And the claim is that, so you may wonder if this is the same as homology with compact supports on a fixed point locus in inconstructible complex. And the claim is that this is completely false. So, and the main reason for the failure is the failure of this kind of what I would call a categorical unit formula. So if you have a y1 and y2, there is still an operation of external tensor product. It's fully faithful, but it's not an equivalence. So like this unit will not be defined as an object of the tensor product, and this computation completely breaks down. So none of it works. However, so here comes a pretty surprising result, which is the main result of our work. And it's the following thing. So theorem, joined with the people that I mentioned, it's the following thing. So now we take our ground field to be FQ bar. However, we assume that my curve and my group are defined over with Q. So everything carries an action of the Frobenius. And I am interested in computing the trace of the Frobenius back on my category of sheaves on 1G, but not the entire category sheaves with nilpotent singular support. So as I said, if I were to attempt to compute the trace, so phi is the Frobenius. So if I were to attempt to compute this trace on the entire category, I'll completely fail. But now I'm replacing this entire category of sheaves, but sheaves with nilpotent singular support. The claim is that some miracle occurs, and if you can compute the trace, you get the answer that you would have expected based on the Betti situation. So the claim is that it is compactly supported cohomology, which I'll decipher in a moment, on the specifically stack of Frobenius fixed points with constant coefficients. But what does it mean? Frobenius fixed points on a stack over a Q is just, well, discrete object of FQ points. So in other words, this is the space of automorphic functions with compact supports. So in other words, this is what I would call autom. It's unramified automorphic functions corresponding to our function field. So this is the main theorem. So, and again, and this is kind of maybe the first real connection between the geometric theory and the classical theory. It says that if you take this geometric category of automorphic sheaves with nilpotent single support, and if you take the categorical trace on it, you recover the automorphic, so you recover the classical category of automorphic forms. So prior to this theorem, our connection between the geometric and the classical was as follows. We used Grothendieck's dictionary. We said that if you have just a sheaf on Bungie with a vase structure, you can take its pointwise trace of the Frobenius and obtain an automorphic function. It was like object by object. But this theory tells you that the entire vector space of automorphic functions is algorithmically recovered from the category. In particular, if you say something about the structure of the category, you will be able to translate it to an assertion about automorphic functions, which is what I will do in the remaining 5 minutes of my talk. So I will now combine this theorem with the geometric Langlands conjecture, as I stated it 15 minutes ago, and we'll see what we get. So let's combine the above theorem Langlands conjecture restricted. And what we obtain is the following. So we obtain that the trace of Frobenius, which has its induced action of incoherent sheaves with nilpotent singular support. This lox is restricted. Is the category of automorphic functions. So this is corollary conjecture. Now I'll decipher what the right-hand side is, and what we're going to do, we'll obtain an explicit description of the space of automorphic functions in Galois terms. And again, it's maybe the first time that we have a closed expression that we say that automorphic functions can be expressed algorithmically through Langlands parameters. So I'll write it in a moment. So up here, I ran a computation of the trace of pullback of an endomorphism in the Betti context. A completely parallel calculation happens for coherent sheaves. So if you have an algebraic stack of variety of an endomorphism, you can compute the trace P upper star on the category of quasi-coherent sheaves on Y. And what you will see well, global sections derived, of course, on the fixed point locals of the structure sheaf. So now I take my Y to be this local system restricted. And now I give another definition. And so now I'm over FQ bar, but everything has an action to the Frobenius, and I can take fixed points. So I define loxis arithmetic to be just fixed point stack on this restricted. So this is what I propose as a definition of the stack of Langlands parameters in the function field case. So now I should say that there have been two alternative definitions of this object, one by Xin-Wen Zhu, another by Peter Scholze. And so they are, so I claim that they are equivalent. So their definitions are completely different, but it's not difficult to show that they actually produce the same object. So we arrived to this definition via the Stanakian formalism, and so Scholze arrived to it via condensed math, but it's ultimately the geometric object is the same. So based on this calculation, we obtained that the trace P upper star on the category of quasi-coherent sheaves on loxis restricted is global sections of the structure sheaf on what I'll define as loxis arithmetic. However, here is kind of the one time in my talk where it becomes important that what the right-hand side is. So it's not quasi-coherent sheaves, but it's incoherent sheaves. And there is, so we state in the paper as a conjecture, but in fact it's easily provable conjecture. Called Rham. That the trace of Frobenius upper star specifically on this modification of quasi-coherent sheaves will produce a slightly different answer, but the slightly has to be taken with a grain of salt. It's global sections, but not of the structure sheaf, but of the dualizing sheaf. And so you may say, what's the big deal? But it's actually a big deal because, so this guy is a locally complete intersection, but this is fixed point set on the locally complete intersection, and it's what we call quasi-smooth. So the structure sheaf of this guy goes infinitely off to the left, and the dualizing sheaf of this guy goes infinitely off to the right. So O and omega very, very different on this time. And so combined with this lemma, we obtain that this is global sections on the stack of Langlands parameters in the arithmetic sense of omega. So again, if you combine it with the geometric Langlands conjecture, which, as I said, is very close to being a theorem already, we obtain a closed expression for the space of automorphic functions. That you take the space of Langlands parameters, you take the dualizing sheaf, and you take its global sections. All right, that's the end of my talk.
Questions from audience?
In the beginning of your lecture, you explained that Langlands correspondence should exist in all kind of realizations in the Rham, Betti, Elatic. But when you go to Elatic realization, you have more structure because you have the action of the arithmetic Galois group, and you were talking in the end about this. It's the case of FP, yeah.
Yes.
So, but what is a more? Is there a more general picture of what happens when you have? Oh, first of all, if you have it's two questions in one. First of all, if you may have not necessarily FP, but some other field, but even better, you can consider Hodge. So you can consider the usual, the arithmetic Galois group or the Hodge Galois group. I would say a real Hodge Galois group. No, but is there some?
So it has to be explored. So this is, we don't know, but must be explored. So let me just say that this trace theorem is very specific to the Frobenius. Okay, open questions, what you're saying.
So this theorem is a case when you have finite field and
yes, this theorem is very specific. It stays to the Frobenius, and so Hodge will be the next step to explore the structures that one gets.
You said Hodge.
Hodge, yes.
Because in the Hodge case, there is action of C star. If your local system is reducible, you have Simpson action. But if it's not reducible, it's a Hodge Galois group action.
So the last equality of function spaces, can you, with automorphic forms. So what are the consequences of this on the multiplicities of a given automorphic representation?
So one can predict multiplicity because you're looking completely at the Galois on the Galois side, and you can say. So we haven't drawn. So again, we should talk. So I haven't. We should see what we can pinpoint. So let me also say that. So I stated it. Bungie and ramified situation. The same story goes through the Iwahori level, and I have 99.9% confidence that it goes through with the epipelagic case, like in your talk, kind of arbitrary number of epipelagic points on the curve. So I'm very confident that the same applies. We can try to draw conclusions.
Okay, any questions from Zoom? All right, let's thank the speaker again. Our next talk will start in 10 minutes, so it'll be 10:45.
The next one's also. I don't know if we can get to Yatsen. Sure. Yeah.
Even the particles from the thousand.